In this video, we're going to cover sections 2.1, 2.2, and 2.3. We're going to discuss different ways in which we can represent organic molecules. So chemists use different ways, different styles to draw molecules. You've seen some of these in earlier courses, whether it was high school chem or Chem 104. And you may have started out learning a lot about molecular formula because they identify the number and the types of atoms that are found in a particular molecule. Now, there are various ways in which we can express how individual atoms are bound to one another within those molecules. We have condensed structures, which provide a little bit of clarity with respect to bonding, partially condensed structures, which show carbon-carbon bonding, but not bonds to the individual hydrogens. And by far the most explicit is the Lewis structure, where basically every bond is shown as a solid line, and electrons that are non-bonding pairs of electrons are shown by dots. And so in Chem 104, you would have learned the Lewis dot structures, and eventually you would have dropped dots to represent bonds and showed those with solid lines. Now these structures, they're really only practical for small molecules. When you start drawing molecules that are larger in size, these types of drawings become somewhat cumbersome and time-consuming. So we have what's known as bond line structures, which are simplified and more concise and succinct with respect to drawing. The other problem with molecular formulas is that they provide no information about structure. They just, again, tell you the number and types of atoms found in the molecule, but do not give you any identifying features as to whether or not you have sigma or pi bonds or which elements are bound to what. So let's look at bond line structures in more detail. Bond line structures simplify the drawing process and are also easier to read. In this example, we have amoxicillin, which is a well-known antibiotic. And what's shown here is the Lewis structure for it. We show all the bonds between carbon, nitrogen, and oxygen to the hydrogens. We show all the lone pairs associated with heteroatoms like oxygen, nitrogen, and sulfur. The bond line structure, on the other hand, is this structure. And you can see that it's much easier to see the relative bonding between neighboring elements. So in line bond structures, we don't show the carbon backbone. We'll show when heteroatoms like nitrogen, sulfur, and oxygen are present, but we don't show the carbons, nor do we show any of the explicit bonds to hydrogen, unless those are to oxygen, nitrogen, and sulfur, heteroatoms of that sort. So it's a much easier way of drawing structures, less time consuming, and much easier to read. So how do we draw bond line structures? Well, bond line structures are drawn in a zigzag format, where each corner or endpoint represents a carbon atom. So in this particular example, we have 1, 2, 3, 4, 5, 6 carbons, which would give us the structure of N-hexane. And so you can see that we're not showing any explicit bonds to hydrogen, and we're not showing carbon as a part of that backbone. Doing either, showing explicit hydrogens or showing the carbons, would be an incorrect bond line structure. It's really important that you become familiar with drawing bond line structures in this way, where the only time we would signify an element is if it's something other than carbon, so nitrogen, oxygen, for example, or the halogens, basically anything else. And we only show hydrogens when they're directly attached to those heteroatoms. You can see below that double and triple bonds are shown by a second line between the 2 points in which that carbon double bond exists. And triple bonds are shown in a similar fashion, where we have 1, 2, 3 lines between those two carbon points. It's also important to remember, and I'll remind you when we look at alkynes later in the semester, is that when we're drawing our alkynes, because of the sp hybridized geometry associated with the two carbons of the alkynes functional group, the next atom bound to that carbon of the alkyne comes straight out in a 180-degree linear manner because of that sp hybridization. So for sp2 hybridized systems, this is seen or thought of as being planar. And again, that falls back to an earlier video where we're talking about the planarity associated with sp2 hybridized systems. And again, the linearity associated with the sp hybridized systems. Again, hydrogen atoms bound to carbon are not shown because it is assumed that each carbon atom will possess enough hydrogen atoms so as to achieve a total of 4 bonds. Now, technically, in a bond-line structure, we don't include these lone pairs on the oxygen. We would normally show this structure as simply the carbon-oxygen backbone without any lone pairs present. So let's look at an example where, if given a Lewis structure, convert that Lewis structure to a bond-line structure. So I've drawn this particular Lewis structure for us to look at. And so now we want to convert this to a bond-line structure. As you can see in the Lewis, we have all the hydrogens being shown that are attached to each of the carbons in the carbon backbone. We show lone pairs on the oxygen and on the nitrogen. And we show all the bonds between carbons and between carbons and nitrogens and so forth. So we explicitly show absolutely everything in our Lewis structure. So if we were to convert that to the bond line structure, let's start with our carbonyl. So our carbonyl is our carbon double bond oxygen. Again, we don't show carbon with the letter C. That's indicated by the intersection of these two lines, this line with this line. So this point represents the carbon in our bond line structure. And let's go from there. So we have this carbon attached to a carbon on the left side. On the left side, that carbon is branched. We have this CH3 group attached to the carbon next to the carbon of the carbonyl. And then we have this fragment, the CH2 CH3 group. So we have to show that. And so you can see we've drawn in our carbonyl attached to that neighboring carbon, which is this carbon here. We have a branching, meaning we have the carbon being bound to at least two other carbons, sometimes 3. But in this case, we have a methyl group, CH3, that's shown by this line, and an ethyl group attached to that carbon, or a CH2 CH3 group, and that's shown by this. So if we continue on the opposite side, the right side, what's directly attached to the carbon of the carbonyl is a nitrogen. To that nitrogen, we have yet another ethyl group, a CH2 CH3 group, as well as the hydrogen. And again, we have to explicitly show bonds to hydrogen of heteroatoms like nitrogen and oxygen. So continuing, we can show that hydrogen, and then we have our ethyl group. And so that completes our bond line structure. We have shown the heteroatoms, oxygen and nitrogen. We've shown hydrogens to the heteroatoms if that's applicable, but all the other carbons in the structure, or all the carbons in the structure, are shown with our bond line structure. No hydrogens are shown unless they're directly attached to something other than carbon. And as a final note, as you've noticed, I've not included any lone pairs around oxygen or nitrogen, and that's typical of a bond line structure, the correct way of showing one. Now in this section, we'd like to continue talking about bond line structures, but now introduce you to the concept of formal charge. Formal charge is really a way of assessing whether an atomic center is electron deficient or electron rich. Electron deficient meaning that it has less valence electrons than it normally has in its neutral state, or electron rich in that it has an additional electron associated with its valence shell compared to its neutral state. So a formal charge is associated with any atom that does not exhibit the appropriate number of valence electrons. So the appropriate number is the number of electrons found in that outermost shell, the valence electrons, associated with a neutral system. So for carbon, that number is 4, nitrogen, that number is 5, oxygen 6, and so on. And so it's important to recognize in your bond line structures whether or not a carbon or nitrogen or oxygen center has one electron less than it normally has in its neutral state, or one additional electron more than it normally has in its valence state. So for carbon, if a carbon had one fewer electrons in its valence shell, meaning not 4 but 3, then the formal charge associated with that carbon atom would be +1. Now, formal charges, we need to show these in bond line structures. Otherwise, the structure is simply incorrect because we're not identifying clearly enough or accurately enough the number of electrons associated with that carbon or atomic center. So when a carbon atom bears a formal charge, whether it's positive or negative, one rule of thumb is that it will always have 3 bonds rather than 4. So let's look at some examples where carbon either bears a formal charge that is positive or negative. Again, this is just highlighting whether or not the carbon atom has one less electron than its normal 4 valence, or one additional electron than its normal valence. So for a carbocation, it's a compound that contains a positively charged carbon atom. And so that identifies this particular carbon center as being deficient by a single electron. So in these carbocation structures, what are not being shown are the hydrogens directly attached to the carbocation centers, because that is one of the main constraints or rules associated with bond line structures, is that we don't show the carbons of the carbon backbone, and we don't show any hydrogens attached to carbon. So in this example, there are 3 bonds to neighboring methyl groups. Because this carbon is electron deficient, it's a carbocation, we would expect, or what this structure is showing us, is that there are no hydrogens attached to that central carbon. However, if we look at this example for carbocation, what is shown is 2 bonds to neighboring carbon groups. So we have a methyl group here, and a CH2-CH3 group, or what's referred to as an ethyl group. But what would be located and attached to this carbon center would be a bond to hydrogen. But again, we don't explicitly show that because we're drawing a bond line structure. Finally, in this example of a carbocation, we see that we have a CH2, CH2, CH3. This propyl group is attached to this deficient carbocation center. And what is not being shown are 2 hydrogen atoms that would also be covalently bound to that carbocation center. When a carbon atom has a formal charge of -1, we refer to these structures as carbanions. And what's shown here is the simplest example, a CH3-. So again, we only have 3 bonds to neighboring atoms, and in that 4th orbital It's not empty as like we see with the carbocation, but it contains a pair of electrons. And so that gives the overall formal charge for this carbon atom a value of -1. You may also recall a simple formula for calculating formal charge in which you start with the number of valence electrons for the particular atom. And for carbon, that will always be 4, nitrogen 5, oxygen 6, and so on. So 4 electrons minus any electrons which are non-bonding. So they're typically as non-bonding pairs, but just specifically non-bonding electrons. So in this particular example, we have 2 non-bonding electrons. And so that will give rise to a -2, representing those 2 non-bonding electrons around that central atom, carbon. And finally, we have to subtract from that as well the total number of electrons that are found in covalent bonds. So we have 2 here, 2 here, 2 here to each of the hydrogens. And so therefore, it's a -1/2 the total number of electrons found in covalent bonds. So -1/2, 6. So if we take 4 minus 2 minus 1/2 of 6, that's going to give us a -1 formal charge. And so we will indicate that with, again, our negative sign. Now, because this is the simplest example of a carbanion, we can't use a bond line structure to show it. But if we were to, let's say, have this particular structure, this would be your Lewis structure for this particular carbanion. If we were to reproduce this as a bond line structure, then we would show it as such. And so we don't need to show the lone pairs. We were given that information in our Lewis structure. And so this formal charge of -1 indicates to us that there are lone pairs at that particular carbon, and that the remaining other bonds to that carbon are 1 to this methyl group, which was this, and the other 2 to hydrogen shown here. So this would be the bond line structure for the ethanide carbanion. So as we saw in the last example, it's important to know when lone pairs are present in a structure, even if we do not formally show them in our bond line structures. We need to know that information so we can calculate accurately the actual formal charge for a particular atomic center. So in this example here, this would be a fairly ambiguous structure because we see that this nitrogen only has 2 bonds to this neighboring carbon. If there was a 3rd bond to hydrogen, we would explicitly show it for nitrogen. So in the case of nitrogen, it's unclear to us without the presence of these lone pairs as whether or not this nitrogen is carrying a formal charge of -1 because there are 2 lone pairs associated with that nitrogen center, or if this formal charge is +1 because there's only a single lone pair and this nitrogen center is deficient by a single electron. So in our textbook in tables 2.2 and 2.3, they provide various examples of oxygen and nitrogen containing compounds where the oxygen or nitrogen is either in a neutral state, contains a formal charge of -1, or a formal charge of +1. And so there's some generalizations that we can make in that when you have an oxygen that has a formal charge of -1 and a single bond to a neighboring element as shown here, that would imply that there are 3 lone pairs around that particular oxygen center. And again, using our simplified formula, there are 6 valence electrons associated with oxygen in its neutral state. In this example, we have 3 non-bonding pairs 2 electrons in each pair. So that gives us a -6. And we have one shared electron in a covalent bond with the neighboring carbon atom. So -1/2 of 2, that gives us again a -1 formal charge. In this next example, we see that these are examples where we have oxygen in its neutral state. And again, no formal charges associated with these oxygens, and so we would assume there are 2 lone pairs associated with that oxygen. That is the preference for oxygen. As we mentioned in the previous section, oxygen normally has 2 bonds to its neighbors in its neutral state and 2 lone pairs. Now, in situations where oxygen forms 3 bonds to its nearest neighbors and 1 lone pair associated with that oxygen center, in those situations, we'll have a formal charge of +1 associated with that oxygen center. And again, we can do that simple calculation where, again, we have 6 for the number of valence electrons formed in the neutral state for oxygen, minus 1 non-bonding pair, minus 1/2 the number of electrons found in covalent bonds to that oxygen center. In this example, there are 3, so that will get us a total of 6. And again, we do that calculation, we end up with a +1 formal charge. So in table 2.3, here are some examples of nitrogen carrying either a formal charge of -1, no charge, or a formal charge of +1. So for nitrogen, when it carries a formal charge of -1, that implies that there are 2 bonds to that nitrogen and 2 lone pairs. If there are 3 bonds and 1 lone pair, that is the neutral state, as shown here. Again, the bond line structure is shown to the left. And if we have 4 bonds to a nitrogen center, there'll be no lone pairs associated with that nitrogen center. And so therefore, the formal charge will be +1. One last point I'd like to make is that we're not to violate the octet rule, which basically states that for second row elements, we cannot have more than 8 electrons in its valence shell. And so elements like carbon, nitrogen, and oxygen can only have a total of 8 electrons involved in either bonding pairs or non-bonding pairs of electrons. So let's look at a couple examples. We'll start with some semi-bond line structures that contain the lone pairs, and we'll use that information to determine the formal charges at each of those atomic centers. And then we'll redraw the proper bond line structure, including the formal charges that are missing in these structures. So if we look at our top structure, we have oxygen with 2 lone pairs and 2 bonds to it. We have another oxygen center with 3 lone pairs and a single bond. And so we can look at the tables, or we can use our simplified formula for formal charge to determine the formal charge at these 2 centers. So for this particular oxygen, oxygen has 6 valence electrons in its neutral state, minus the 4 non-bonding electrons around it. That would give us 2, minus the 1/2 of the 4 electrons involved in covalent bonds to that neighboring carbon. So oxygen in this state, with 2 lone pairs and 2 covalent bonds, would have a neutral formal charge. And so that does not need a formal charge. This oxygen, however, has 3 lone pairs and only 1 covalent bond to that same carbon. And so again, if we use our formula, 6 minus the 6 non-bonding electrons minus 1/2 the 2 electrons found in that bond to carbon, we end up with a formal charge of -1. And so if we're to redraw this structure, including its formal charges and dropping our lone pairs, this is the proper bond line structure with a -1 formal charge on that oxygen center. If we go to the second example, here we have a oxygen center that has 3 bonds, 3 covalent bonds, each to hydrogen, and we have a single lone pair. And so again, we can calculate this out. Again, this will become more familiar the more you look at these structures in detail, but we can start with our calculation, -2 minus 1/2, 6. And so in this example, we're going to have a +1 formal charge on that oxygen center. And so we would normally show that in this way, where we have our +1 formal charge drawn next to the oxygen because there are 3 covalent bonds in a single lone pair. Now, starting out, it'll be common to show our bond line structures in this way, but as you become more familiar, it's important to represent the bond line structures without those lone pairs being shown explicitly. So if we look at a couple examples with nitrogen, here we have a nitrogen center with a single lone pair and 3 bonds to its nearest neighbors. And so if we carry out our calculation, number of valence electrons around a normal nitrogen center is 5, -2 in our non-bonding pair, and -1/2, 6 found in covalent bonds to the neighboring carbons. And so that will give us a formal charge of 0. So nitrogen in this form, single non-bonding pair and 3 covalent bonds, will have a neutral formal charge. And so if we were to redraw this structure, not showing our lone pair, it would simply be this. And so in many ways, these are equivalent, although this is the more accurate bond line structure because it doesn't explicitly show the lone pairs. In our structure right below, here we have nitrogen with 4 neighboring covalent bonds. And so again, there are no lone pairs being shown explicitly. And we have 8 electrons found in covalent bonds to that nitrogen center. And so in this example, that nitrogen center will have a formal charge of +1. So nitrogen in this example, we don't have to redraw it because there's no lone pairs present, but we have to include the formal charge. So that would be the proper bond line structure, including its. The last section in this video is section 2.3 on 3-dimensional bond line structures. Bond line structures with wedges and dashes indicate 3-dimensionality. So if we wish to show the 3 dimensions of a particular molecule on a 2-dimensional page, we need to use solid wedges and dashes to represent that 3-dimensionality. So if we look at the 2 examples shown here, we have an acyclic, implying no ring system, and a cyclic system, where we have a single cyclohexane ring. But more importantly, we see that this carbon-chlorine bond, we draw a solid wedge. When we draw the solid wedge, it implies that this chlorine is coming out of the page towards you. Whereas this carbon-chlorine bond, we use a dash wedge, and it implies that the bond is below the page or behind the page. And in that way, we show 3-dimensional structure of a molecule on a 2-dimensional surface on our page. In this ring system, similarly, we see a solid wedge between this carbon and oxygen of this hydroxyl group, and that represents that this OH group is above the plane of this ring, above the page, whereas this particular OH group attached to the ring system would be behind the page or sitting below the plane of that ring. It's important to recognize that all organic compounds have a 3-dimensional structure. And the use of these solid wedges and dashes can be important to show that three-dimensionality when drawing a structure on a two-dimensional surface. Even the simplest tetrahedral could be drawn in a three-dimensional manner, which clearly shows the angles associated with tetrahedral that we discussed in the last section. Recall that all the carbon-carbon-carbon angles in a tetrahedral are approximately 109.5 degrees. Using these solid wedges and dash wedges clearly shows that there is that three-dimensionality with this structure. We'll see more of this when we start to look at various organic compounds that have chiral centers and different isomers within ring systems. So if you have any questions about this video with regard to the drawing of bond-line structures, determining formal charges and including those in your bond-line structures, or the drawing of three-dimensional bond-line structures, please send me an email or start a discussion in our forum. Thank you.